Hello? Hello? Sounds to me like the audio is working. Video. Yes, I'm on there twice. Okay. You got the video on? That's up. That's up. This is up. Share the desktop. Okay, so we should be broadcasting. If anybody's on distance, I guess we got Art and Troy and Doug. If you guys could just type a chat and let me know if you're hearing the audio. It sounds to me like the audio is coming through from my computer. You could just confirm whether or not you're hearing anything. Hello, hello, hello. Sounds like, according to Wimba, it looks like the audio is up too high. Is it being overdriven? Maybe y'all just aren't paying attention. Maybe that's it. Audio seems fine. Fantastic. All right. Okay, so let's get started. I think we have all the electronic gizmos set up. Success point number 1. Y'all are still here. I haven't chased y'all off yet, so this is good. Okay. So, Lab 0 is posted. Hope you've had a chance to look at it. We're going to talk just a little bit about some logistical information, and then we'll dive into a discussion that relates to Lab 0. Okay. First off, we have labs in this class. I hope that I've beaten that one into your head so far. The lab room, we will be making use of Engineering 328. That's the micron imaging lab. It's downstairs, back in that back corner of the building here. Okay. You'll be getting intimately familiar with that room as the semester proceeds. This lab, you don't need to be in that room to do it. A lot of the labs, you can do most of it outside of that lab room. What that lab room will contain, number 1, is a TA named Rohit. He's my PhD student. He has TA'd for the class before, and he knows his stuff. He will be there tomorrow from, 10:30 to 4:15. There'll be a gap in there where he goes off and does lunch at some point, but for the most part, he's going to be in the lab tomorrow during those hours, so you can come and ask questions. Okay? The vote is swinging to Tuesday for our regular lab times. I did realize that some of you may have been misled in that just because I have a lab that's due on Monday for Lab 0, not all the labs are always going to be due on Monday. Okay? The day that they're due will probably move around during the course of the semester, depending on where we're at and how much time I can allocate to a given lab. So I always try to give you as much time as we can possibly afford so that you can do the lab, but due dates are going to shift. Okay? Once I give you the lab, the due date probably won't shift too much, but I'm not going to say that labs will always be due on Monday. So given that, does anybody want to change their vote? Good. Sorry, voting closed. So we are running at about 12 votes for Tuesday and about 7 votes for Thursday. So there's going to have to be pretty much a major swing in order to swing us to something else. And I'm not opposed, and Rohit, I'm sure, won't be opposed if we decide we want to switch it somewhere in the middle of the semester, too. Okay? All right. So we will be getting you guys key card access to 328. I'll be bringing forms that, this is the painful part, that I've got to sign a form for each one of you guys to give you access to the lab. So we'll get that taken care of. How will he address questions for distance students? We're going to try to run WIMBA now. So he will be running a WIMBA session. So if you want to just log into WIMBA and ask him a question via text message or something like excuse me. If you want to ask him a question via the chat on WIMBA remotely, whether you're a distance student or not, that's your prerogative. You can do that. But we are going to try, and I'm sure we're going to have to work some kinks out of that, but we're going to try to run a WIMBA session every time he's in a lab so that if you are remote accessing, you can ask questions of the lab TA. Okay? All right, next issue. If you want to buy or have to buy a TS7200 board, what do you need to get? So for Lab 0, we don't need a TS7200 board. For Lab 1 and beyond, we will need a TS7200 board. Okay? So, like I said last time, there's the option to purchase them. For those of you who are on campus, for those of you who are distant, the arrangement is that you need to buy one. Okay? Or borrow one from somebody who's taken the class before. So what do you need to get? So you go to www.embeddedarm.com. That's a website for Technologic Systems. That's the company that manufactures the board that we make. There are 3 things that you need to get. The first one is the board, the TS7200 328F. That means it's got 32 megabytes of RAM and 8 megabytes of flash. Okay? One board costs $150. If you want to buy 100 of them, you can get them for $120 a piece. I'm sure you all need 100 of these boards kicking around. Okay. You need the serial null modem cable of DB9 connectors. That's that part number CD7-05, $9. And you need the power supply. So 5-volt DC power supplies. This is a plug that plugs into the wall that just supplies power to the board. And that's $22. So anyway, those are the 3 things that you need. If you want to get a dev kit, fine, get a dev kit. It's useful, especially if you want to putter around with the board later on. But the serial cable and the power supply are both included in the dev kit. So if you go with the dev kit, don't get separately the serial cable and the power supply. But you don't need to have the dev kit to do what we're doing in class. Okay. Any questions about lab or any logistical information? So just remember, Rohit's going to be in the lab tomorrow. I will probably show my face in there once or twice as well, just to see how things are going. All right. We are going to now talk a little bit about software construction. How many of y'all have started the lab? Figured out how to spell FIFO? How many of you could tell me what is a FIFO? That's what it stands for. That doesn't say what it is. What is a FIFO? Who wants to answer by pushing the button on their microphone? Mitch.
A data structure.
You don't need to be that close. It is a data structure. Anybody care to elaborate on what we mean by data structure, or be perhaps a little bit more specific than just saying it's a data structure? We have lots of data structures. What's a FIFO data structure? Mitch?
A queue?
A queue?
Kind of.
Is there a difference between a queue and a FIFO?
A queue is a type of FIFO, or I mean, other way around.
Okay. It's a big difference if you're playing Scrabble. Queue's worth a lot more points. Okay. Queue, there's not necessarily anything saying you have to have first in, first out, but it's an ordered list where everything goes in the same direction. Okay, you can put it in the back end and have it come out the front end if you want to. But effectively the same thing. Okay, so a FIFO, you think about it as a collection of objects, a collection of items, a collection of pieces of data. Okay? What do we mean collection? Well, let's just say, so for example, in Lab 0, we've got a bunch of integers. We're going to be storing those integers. We want to hold them all. We don't know how many integers we're going to have beforehand, so we've got to have a data structure that is permitted to grow as needed. Okay? So, mess up that view. Let's see how this does. First in, first out data structure. Okay? You use it when you have a set of data that you need to hold. You don't know how much data you're going to have beforehand. If you know how much data you're going to have beforehand, what type of structure should you use to store the data? An array. Okay? What if you want to sort the data? Is an array appropriate? Yeah? Yeah? What's the disadvantage of using a non-array to hold the data? Takes more memory. Okay? Any other disadvantages? Okay, to access an object, you've got to go through so many objects. It depends on how you implement the FIFO. Because you don't have to implement the FIFO using a list. You can implement a FIFO using an array. But what we think about here is a linked list. If we want to store 8, 7, 6, 5 in a FIFO data structure. Okay, so if we want to store 8, 7, 6, 5 in a FIFO data structure, which one of those numbers goes here? 8, 8, 8. Do I hear 5, 5, 5, 5? Do I hear 8, 8, 8, 8, 8, 8, 5? It depends on what the definition of first is. Who's first? Who's on first? What's on second? I don't know who's on third. Okay. Which one? So do we insert? So the FIFO data structure is actually two pointers. It's got a pointer to head and a pointer to tail. Okay? If we say that we insert at the front and we remove from the tail, who should go in first? Who should be placed here? The guy that we most recently inserted. So if we received 8, then 7, then 6, then 5, this list goes 8, 7, 6, 5. Head, tail. So if we insert at head, receive 8, then 7, then 6, then 5. Why is it like this? Well, because when we receive an 8, we create a single list node. So on receipt of 8, we end up with a FIFO that looks like 8. Okay? Then when we receive 7, we push 8 back. Okay? When you receive 6, I think you can see the pattern here. Okay, so we just go on building our list like this. We keep on inserting stuff. With a FIFO, there's nothing saying you have to insert all your items and only then can you start to remove stuff. You can remove stuff as you're inserting stuff. The data structure itself doesn't care. It supports both operations. Okay? And your implementation of the FIFO data structure has to support insertions intermixed with removal. Okay? However, the driver program that we're writing only inserts a bunch of numbers, then removes a bunch of numbers. So the driver program that I've asked you to write for Lab 0 doesn't actually explicitly intermix insertions and removals. Okay. Let's talk a little bit about FIFOs and software. We've got this data structure for holding things. So let's consider the implementation of this data structure. We've got FIFO.h, FIFO.c, FIFO main.c. Okay, what is the purpose of these different files? FIFO.h. FIFO.h is a header file. It defines data structures. It defines function prototypes. Does it contain function implementations? No. What else does it have?
Macros.
Might have macros. Have pound defines. Have comments. Documenting what the functions are used for. Okay. But what the purpose of FIFO.h is it defines an interface to a FIFO module. Okay. Then we have FIFO.c, which is a source file that contains the implementations of the functions that are defined in FIFO.h. Okay. So the implementation of create FIFO, the implementation of FIFO insert, all of the functions that are defined in FIFO.h, the implementations need to be put in FIFO.c. They are not put in FIFO main.c. Why do we separate those guys? That's the question that we're going to be addressing. FIFO main.c is a source file that contains the code which uses the FIFO module. Okay, so in FIFO main.c we have the functions that call the functions in FIFO.h. In FIFO.c we have the implementations of the functions in FIFO.h. We keep those two guys separated. Okay? The way you need to think about developing software from this point on in your entire life is this. Okay? You are all now ostriches. You all now have a hole in the ground, and when it comes to implementing software, if you are the module implementer, you put your head right in the ground. You go, la 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 la, I don't know anything about implementation. I don't know anything about users. I don't know anything about clients. All I know is about my implementation. Okay? The interface is a wall in between your module client and your module implementer, your module implementation. This is FIFO.c. This is FIFO main.c. We want to separate these two guys out, put a wall in between them. The only way that the client code, the code that uses the FIFO module, can access whatever the FIFO does is through the functions that are defined in FIFO.h. The module implementation does not access any code that's over here in your FIFO client. Okay? So this guy just takes care of his own business. He implements the services that are defined in the API. The client uses those services but does not define any services. You do this out of good practice in C. In Java and C++, there are structures in the language which formally support this notion. There is some notion of support for this in C, but you have to do it the right way. But C is very content if you go and do it the wrong way. Okay? And I'm sure that left to your own devices, and including the rest of the semester, some of you are going to choose to do it the wrong way. But I want you to think about this and keep this in mind. This is the principle of modularity. You define services in software modules and you separate them so that you've got client code that uses the services, implementation code that defines and implements those services, and a well-defined interface that separates the two. Okay. Now the question that I have for you is, So we've said that we want to separate these two. Come on down here. Move, move, move. Hello. Sorry, Wimba froze a bit. There we go. Why do we want to separate our software like this? Why do you want to be Mr. Ostrich if you are the guy that's implementing FIFO.C and stick your head straight in the ground and you don't want to be aware of what the client code is actually doing? Is ignorance bliss? Yeah.
Makes it reusable.
Jonathan, right?
Yep.
Okay. So say it again.
Makes it reusable.
Makes it reusable. Which it?
The module.
Makes the module reusable. Okay. Anybody care to offer more of an explanation on that argument, or offer other points of benefit of why we want to do this, why we want to be an ostrich?
Easy to debug later.
Easy to debug. Okay. And use the mic. That's okay. I forgot to. Any other reasons? Easier to debug. Brad's aiming, thinking, maybe. Itchy trigger finger, maybe not.
Mine's on.
Mitch.
Replaceable.
Replaceable. What's replaceable?
The module.
Okay. So here's the deal. How many, at the end of the day, how many FIFO.Cs are we going to have when you guys submit Lab 0? Me. I had better have a bunch. If I have 2, then I've successfully scared y'all off. Okay? I had better have 20 of them. If I want to test your code, how am I going to do it? I'm going to take my FIFO main.c and put in your FIFO.c, and it had better work. Okay? The reason why it had better work is because your code should adhere to that interface. If your FIFO.c no worky with my FIFO main.c, you will have a problem. Okay? So that's how we can tell whether or not there's a bug in the system. But more importantly than a classroom setting is if you have different implementations of a module and you find one that has a bug in it, and you've got some other team that's implemented a different implementation but adheres to the same interface, you can swap this out and plug the next one in. All of a sudden, we are now Eli Whitney. We are interchangeable parts. Okay? We are now making software that is maintainable and can be modified. So these issues that you brought up about why is it good? Number one. Here we go. I'd say the first and most important reason is it simplifies things. Because how many lines of code are totally going to be implemented with Lab 0? Well, if you take up maybe 200 lines of code for FIFO main and another 250 for FIFO.C, you have to worry about 500 lines of code all at once, or do you have to worry about 200 lines of code in one chunk and 250 lines of code in another chunk? When you're implementing the module, you don't have to worry about what's going on in the client. When you're implementing the client, you don't have to worry about what's going on in the module. It simplifies your life. Okay? Debugging. The reason why this is good for debugging is because we're attempting to isolate the module definition from the client code. Bugs that are in the client code may manifest themselves looking like they're errors in the module, but the idea is that we're trying to separate these two guys out so that you can develop and debug the module implementation separately from the client implementation. Scalability and reuse. Okay, so how many of y'all in C++ have ever used cout? How many of y'all have ever written cout? How many times has cout been used relative to the number of times it's been written? You say that's a pretty good example of code that gets reused a bunch? Okay, that's an example of why we like modularity, is because you can take a chunk of code, implement it, debug it once, deploy it everywhere. You know, Java aspires to be this. Gag me with a pitchfork. Okay, you can deploy it and have a whole lot of people use it. And that module, as long as it's debugged correctly, which is impossible for Java, as long as it's debugged correctly, you can reuse that sucker, and you can not have to implement cout every time you go to write a program. Okay? So this facilitates scalable software development. Maintenance, we talked about swapping different implementations of the same module. The bottom line is it's just good programming practice. So for Lab 0, I'm making you do this. For the rest of the labs, it's up to you. You should get into the practice of trying to figure out how to hide the implementation details of a module from the client of the module. It's good software practice. It will save your bacon as the labs get more complex. Okay? Okay. Let's talk about program compilation for a little bit. Okay? Suppose we've got int main void, and we call a function foo. We define the prototype to function foo up there. We've got all that in main.c. How does this program run? How many of you have ever used a processor that runs C code? Mitch, you know better. Does a processor run C? How about English? COBOL's pretty close to English. Can a processor run English? How many of y'all are hardware guys? Want to design a processor that runs English? That'd be worse than Java. What language does your processor speak? Garrett, you got a laptop. What language does your processor speak? Machine? Okay, give me an example of machine language. Assembly language? Right? Does a processor run assembly language? What? What do you mean no? How can it not run assembly language? Well, what is it supposed to run then? Somebody rattle me off some program code that'll run on a CPU. 1011100110111111. But wait a minute, am I speaking ASCII? Oh, come on, guys. That's supposed to be a good joke. Definitely have to work on the geek humor here. Okay. CPUs only understand instruction opcodes. They are in binary. They are in ones and zeros. A machine no speak 'em C, no speak 'em assembly, no speak 'em Fortran. Heaven forbid it speak Java, but it will only speak ones and zeros. Okay? So now the question is, how do we go from C to ones and zeros? How many of you all have done this part before? Made a C program into ones and zeros, or a C++ program. How many of y'all have broken arms? How many of y'all have never run a computer program before in your life? You're going to be dead if you've never run a program and you're in this class. Okay. There's a process for building and running programs. And it, here's a hint, is not the build button in Visual Studio. Okay? Sorry to disappoint. There's a whole lot of stuff that goes on under the hood. We have our main.c, our C program. That goes through the CPP. What does CPP stand for? The C preprocessor. Ah, you think it was C++. Who knew? Okay, so we go through the C preprocessor. Then we send the preprocessed output to a compiler. What does a compiler produce? Does it produce object code? It does not. It produces assembly code. Wait a minute, why don't I ever see the assembly code? So if I push the build button on Visual Studio and I take my CPP file and I've got Hello World running, why don't I ever get hello.s or hello.asm or whatever? Compiler tools are nice. They create the file and then delete it for you. You know, because you don't need that file. But wait a minute, what is it doing then? It creates the assembly file, so it's going to create a file and then delete it. What does it do in the meantime? Well, okay. So the compiler creates main.s, that's the assembly file, and then it passes it on to an assembler. Okay? That assembler then assembles the file that creates main.o. What is main.o? Object code. That's your object file. Can you run an object file? Sometimes, under very rare circumstances. If you have no dependencies on operating system calls, then sure. Well, unless, of course, you're having linker issues that change file formats and other fun things like that. But anyway, so you get your object code, and then that passes to the link stage. What does your linker do? Takes an object file and outputs an executable. Does it do anything? Well, you're going to see. Okay. The other thing you've got to think about is that you've got this build chain right here, the CPP compiler assembler build chain that feeds the linker. Then you have potentially a program that depends on multiple source files. If you have multiple source files, each one of those files goes through a similar chain, preprocess, compile, assemble. Only the linker examines all the files in your program. So if you've got 3 source files, you compile and assemble all of those source files, you've got object files. You're going to then have the linker apply its Elmer's glue and glue all those guys together. It will also take libraries. Those libraries are what implement things like cout or printf. We're going to stop talking about cout so much, and we're going to start talking about printf, okay? Because printf is C. So we take these libraries along with the object files produced from the build process, throw those to the linker. The linker does its waving of the magic wand, and abracadabra, yeah, get out an executable file. Wait, don't I just push build and it all works? Well, yeah. But this is, you remember where we talked about onions? Did we talk about onions? Didn't talk about onions. Okay. So, how many of y'all have seen Shrek? Ogres have layers, donkey! Embedded systems, computer systems are like onions. They have layers, donkey. Okay? So, the layers offer abstractions. Okay? These are way you think about things, the way you look at systems. When you're building using Visual Studio, I hit the build button and magically everything else works. That is one layer of the onion. And I don't have to worry about what's the difference between a compiler and a linker, usually when I'm building small programs and I'm deploying small programs and I'm not focusing on, well, what is this particular nuance of an error as opposed to another one. Okay? What I need to worry about is when do I need to know what's underneath this layer of the onion. So if I peel back that layer of the onion, guess what's under there? Another layer of the onion. You keep on peeling back more and more layers of the onion. These are the different levels at which we can understand and perceive and comprehend what's going on in computer systems. Okay? So one layer of the onion is I just push build and it all works. Another layer of the onion is understanding what's going on in this figure we just talked about. So understanding the difference between the CP processor, the compiler, the assembler, and the linker. There are times where you need to worry about it. There are times where you don't. We are going to dice the onion, you guys, in this class. We are going to dig through every layer there is. You know, I still think transistor is a profanity, so we won't be going down to the transistor level. But we are going to be talking about, when it comes to software development and how computers work, digging down as far down as you can get on hardware on a computer. Okay. I also refer to this as getting underneath the hood. Okay. The various tools in the tool chain. What do they do? What are their responsibilities? We have a preprocessor. The preprocessor resolves preprocessor directives. Pound include, pound if def, pound define, all these other directives. The C preprocessor does not understand C. It doesn't understand C syntax. It might be able to pick up a comment or two, but it doesn't understand for loops or while loops or anything like that. All it understands is its directives. All that the C preprocessor does, you kind of think about this as a source-to-source compilation. What it'll do is, for when you say pound include some file, it goes and it grabs the contents of that file and plunks it in and replaces the pound include statement with the contents of the associated file. It doesn't understand what to do or what those contents mean. It just says, okay, yeah, I'll go get this. I'll go put it right there. Okay, good. Okay, pound define. This does a search and replace for a particular symbol. Pound if def, you can include or exclude text in the file. You know, you could write an English paper using the C preprocessor. Commenting in sections, commenting out sections, pound include this or pound include that. It doesn't care that it's C. Okay? So, but it's a convenient way of helping us prepare our source files to feed it to the compiler. The one thing that's commonly misunderstood about compilers, well, first off, we always blame all of our woes and dumbness when we're developing code on the compiler. The compiler did this or the compiler did that. No, you did it. So what you don't understand, or what commonly is misunderstood about compilers, is that they only work on one file at a time. Okay? You can only compile one source code or one source file at a time. So when you're building your Lab 0, you've got FIFO.c and FIFO main.c. You will compile FIFO.c. The compiler won't see anything from FIFO main.c while it compiles FIFO.c. Likewise, it'll compile FIFO main.c and it won't see any of the code in FIFO.c. Your compiler does not compile a header file. Okay? So when I'm going to use printf, I pound include stdio.h. When I'm going to use the FIFO module, I pound include the FIFO.h. But the pound including happens at preprocess time. So when the preprocessor does its thing, it's going to take your original C file and muck around with it. It's going to modify it. It'll put some stuff in it. That stuff is stuff that you've told it to put in it. And it'll change things around. It'll output an intermediate file that is your post-preprocess file, and that's the file that goes onto the compiler. But it's only one file, one source file. All the pound includes are resolved, and all the preprocessor directives are resolved. But so just remember, the compiler only sees one file at a time. It does not produce object code. It produces assembly code. That assembly code is put into a temporary file that later gets deleted because you're not going to need it later. So it'll produce assembly file that then gets sent to the assembler. Okay. Where this gets you into trouble is when you're thinking about global variables. So if I define a global variable in one source file, and I use a global variable in another source file, how can, when I'm compiling the file that uses that global variable, you know, all the variables have to be declared before they're used. How can I declare that global variable? Because I've already got it declared over there. But I can't declare it again over here because then the linker will tell me I've got two global variables with the same name. So we've got this issue about how do you deal with global variables. Global functions are the same thing. And I'll teach you how to resolve all that stuff. Okay. What's the assembler do? The assembler just takes your assembly code and produces object code. It just does a simple lookup table translation of the mnemonics and the registers, the address modes, and produces object code. Okay. The linker's role is to slap all the object code files together, apply the Elmer's glue, make sure everything works. The linker does not speak C. Linkers theoretically can take a C file or a file that was compiled from C source code and a file that was compiled from C++ source code and can link them together. Okay? There are translations that reduce the input language and eliminate source language specifics and produce something that's close to machine code that the linker can then chew on and output an executable. Okay? The linker's job is to resolve all these globally defined symbols where one module needs a symbol and another module defines a symbol, so it figures out who's got what defined where and who needs what where, and let's make sure that all the addresses are all the same. Okay, the other thing that we need to understand about linkers is that only the linker has global scope. Okay? Only the linker sees multiple files. The compiler does not. The preprocessor doesn't. Well, the preprocessor does to some extent because it's going to see a pound include and it'll go out and grab a second file and put it in. But only the linker sees the code that you've defined in FIFO main.c and the code that you've defined in FIFO.c. Technically, they're not .c's at that point, they're .o's. Okay, so when we're building Lab 0, this is what the build chain looks like. Okay, we start with FIFO main.c, FIFO.c, we have FIFO.h. These cylinders represent files. Okay, we invoke when we're building FIFO.c, we send this through a preprocessor. That pound includes FIFO.h. The preprocessor outputs a file that goes to CC1. That's the name of the GNU compiler collection, C compiler. Okay? CC1 then produces an output file that's an assembly file that goes through AS, which is the GNU Compiler Collections assembler, and then that produces an object file called FIFO.o. Over here, we've got FIFO main.c and FIFO.h that go through a preprocessor, go through CC1, go through an assembler, and produce FIFO main.o. Next, hello, down, 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 come on, Limbo. There we go. Okay. FIFO main.o, FIFO.o go into LD, which is the name of the linker program. The linker then takes libc.a, which is the C runtime library function definitions. That's got the code for things like printf. Links them all together and produces FIFO main.exe. Now, here's a question. Aren't we glad that we don't have to run each of these tools individually? Aren't we glad that we have things like build buttons? Okay? We are going to be developing in a command line environment where there's no such thing as a button. How do I get my build button back? Okay, this is what the purpose of a make file is. So, separate compilation. Separate compilation is this concept where you have got multiple source files. I'm going to compile them separately and then link them together. The reason why separate compilation is a good thing is because if I've got 1,000 files in my program, all separated out nice and neat, and I make a change to one of them, and I have to rebuild the program. With separate compilation, I build that one source file, I send it through the compile and assemble chain, get the object file, and then I relink all of the files together. I do not have to recompile 1,000 files. Okay? That is one benefit of having the ability to compile each file separately. And it says, for big projects, it saves a ton of time. For small projects, it doesn't save you anything. Okay, how do I go about doing this? This is the GNU Compiler Collection, GCC. GCC is a program that runs other programs. It's called a compiler shell. Okay. You can run GCC on a source file named fred.f that would have Fortran code. How many of y'all are Fortran programmers? Fewer and farther between. So Fortran is actually still used quite prevalently. So you can run GCC on Fortran. You can run GCC on C code. You can run GCC on C++ code. Note that the extension on fred.cc, that's for C++. .cc means C++ to the GNU tools. CPP does not mean C++ to the GNU tools. Okay? Okay, so if you just take some source file, fred.c, and you say GCC fred.c, GCC says, oh, you're giving me a source file and you want to produce an executable. So it's going to run the whole build chain, including it's going to run preprocessor, compiler, assembler, and linker and produce you an executable. It'll produce you an executable named a.exe. Why does it produce you something named a.exe? Because you didn't tell it what you wanted it to produce, so it's going to guess, and it's got a default name. Okay? So what about in lab 0? I've got to build FIFO.c and FIFO main.c, and if I just say GCC FIFO.c, it's going to tell me, wait, you don't have a main. Or if I say GCC FIFO main.c, it's going to say, well, I found main, but I don't have implementations for create FIFO, destroy FIFO, all the module implementations that are all in that FIFO.c file. I don't have those. The reason why is because we're doing separate compilation. I don't want to carry FIFO.c through executable. I want to just build it, compile it, assemble it, and then I later want to link it when I can link both FIFO.o with FIFO main.o. So here's what you do. You say GCC -c. This is a switch. That switch tells the compiler, compile the following file, but stop after you're done assembling. Okay? So preprocess, compile, assemble, don't link. Okay, the default output is a.o. Why is it a.o? Because you didn't tell it what you wanted to name the output file. How do you tell it what you want to name the output file? You use the switch -o followed by a name. Okay. So GCC -c FIFO.c -o FIFO.o. This says preprocess, compile, assemble FIFO.c, produce a file named FIFO.o that is an object file. Similarly, we do the same thing for FIFO main. We say compile, assemble, so preprocess, compile, and assemble FIFO main.c to produce FIFO main.o. Now we have to run the linker. How do we run the linker? Well, we just call GCC again. Yeah, Steven.
Is it going to put it in the same directory no matter what, or is there a way to say it to put it in different directories, the output file?
Yeah, so you can tell it to put the output files in different directories if you want to. You just pass a relative path to the -o.
Okay, and once it's linked, can you get rid of those output files? Are they not necessary anymore? Once
The
you
object
have
code?
Yeah, once you have the .exe.
So you can do that. Usually what you do is you have a target in your make file called clean that you tell it, when you're clean, you're going to remove everything that you don't want to have lying around. So you can tell it remove star.o, remove star.exe. But if you're just doing, if you want to by default always remove the object files before you remove the source file, then you can put right after your link stage in your make file, you can put an rm star.o. But you don't want to do that. And the reason why, I will tell you in a moment. Okay. So to link right here, we just call GCC FIFO.o, FIFO main.o, -o, FIFO main.exe. How does GCC know that we want to run the linker on this step instead of the compiler? Because it knows .o means object file. So it says, oh, you want me to run, just like it knows .f means Fortran, and it knows that .o or that .c means C code, then what this means is run the linker. Okay. This invokes the linker. We link it together. We produce FIFO main.exe. So in order to build a program to carry lab 0 all the way through the build chain, we need to run this statement, then that statement. Compile FIFO.c, compile FIFO.o, link FIFO main.o, FIFO.o to produce FIFO main.exe. How do I run the program? At a bash prompt, I say /FIFO main.exe. Why do I need the /? You have to tell the operating system what FIFO main program you're trying to run. // says run the one that's in this directory. It's in my current working directory. Okay? It doesn't assume to look in the current working directory. You have to tell it explicitly. Okay. Don't you think that'd be a pain to have to retype those commands every time you want to build a program? That's just a pain in the neck. Hence why we want to have our build button, which is our make file. Okay? So the make file. The make file is a script containing the commands that you need in order to build your program. Basically, you just think about it as like a batch file that you have those 3 commands typed in there so that it knows what to do every time you want to build your program. But a make file is a little bit smarter than a batch file. It knows how to, for example, if you're building lab 0 and you've tweaked FIFO main.c, but you have not tweaked FIFO.c, it's smart enough if you implement the make file correctly to say, has FIFO main.c changed since the last time I built FIFO main.exe? If it has, then I need to rebuild. I need to send the FIFO.c through the build chain. If FIFO.o has not changed, I don't need to send it. I'll just keep its .o file around. This is why you don't want to remove your object files. So it'll compare the write time of the object file against the write time, or it'll compare the write time of the C file against the write time of the executable. If the C file is older than the executable, I don't need to rebuild the C file. If the C file is newer than the executable, I do need to rebuild the C file and as well as rebuild the executable. So, what is a make file? It's a sequence of, come on, move. Hello, right here. Thank you. Okay. A make file consists of a sequence of these things right here. You have a target, followed by a colon, followed by dependencies, followed by rules. Okay? These guys start on the column on the left side of the file. They're followed by a colon. There's a tab in for each one of the rules. Targets are separated by carriage returns. So if you can have multiple targets in a make file. Dependencies are lists of targets, other targets, or files. Okay? Your targets always begin on the first column. They can be names of files, or they can be just some other name like phase 1 or lab 0 or something like that. Okay. You have a default target that you can put into your make file called all. Okay. You run a make file by typing make. You can also run a make file by typing make followed by a target name. Okay. When you run make, it assumes you're trying to make the target all. So you can type make all or just make. Make just assumes that if you haven't provided a target name, it means all. You typically have a clean target to remove all of the artifacts of the build process, like object files, assembly files, executable files, etc. The dependencies are what need to be up to date when you're going to build a program. So, for example, if you're building FIFO main.exe, you want to make sure FIFO.c is up to date. or you want to make sure that FIFO.O is up to date, and FIFO main.O and FIFO.O are both up to date before you build the executable. What it means to be up to date is that comparing of the file write time business that I told you about. So it'll see, you need this object file. Let me look at the source code file. Let me see the result. I'm building FIFO main.exe. Let me compare the write time when this file was last written on the operating system to the write time of the source file. If they're different, if the source file is newer, that means somebody edited the source file and I need to rebuild it. If it's not newer, that means the file's up to date. So it'll only run rules associated with files that need to be updated. Okay. So what happens is when you say build a target, it'll go and check the dependencies. It'll check to see if all the dependencies are up to date. If all the dependencies are up to date, it will run the corresponding rules. The rules are the commands that follow the dependency list. And the rules specify how you build the target. These can be operating system commands, script commands, programs that you run, or whatever. So this is an example. Okay. Here's the target all. I have the rule, or I have the target main program as my dependent. So what I'm going to say is when I type make, I want to actually build my main program. Main program here, this target has the rule gcc main.c-o main.exe. Okay, so when I say make, that's going to evaluate this target. It'll run this rule, compile main.c to produce main.exe. There's no really dependency evaluation here because this simple make file doesn't have any dependencies. Okay, so make runs the build. It'll just invoke that statement. When you say make clean, it will run this statement. Okay. Okay, so what we want to do, so if we give make some more information, it can do a little bit better. The idea that we want to be able to do is have it not run the build every time unless it needs to. So what we can do is we can say all main.exe, main.exe has this, gcc main.c-o main.exe. So if we run make, it'll run, if we run make the first time, it'll build main.exe. If we then run make again, it'll say main.exe is up to date. And it won't run the build command again because it doesn't need to. The reason why it knows that it doesn't need to is it says this target is the same name as a file. So if this file's up to date, I don't need to run it. Okay? Okay. Lab 0 make file. I showed you the Lab 0 make file last time. What I want you to do in your spare time, take a look at the Lab 0 make file and try to make heads or tails of it. And we'll talk briefly about the Lab 0 make file next time as well. But you're going to need to be proficient. You need to spend tomorrow to work on the lab. Because if you have major questions, Friday's the day. Okay? I have office hours today, but I've got to be late to my office because there's a meeting that I got to go to for the department. That's at 3. I'll probably be in the office by 4. But so please do come by. I'll stay late if I need to talk to you if you've got questions about the lab. Okay. Thanks.